I want to know at point C, what are my internal loads with that orthogonal cut. Now typically, like we saw in 2D, the first step was solve the external problem, just like we start with solving a chapter 5 style problem. And we could do that here also. We look at externally what's happening. We have a built-in connection at A. So at point A, we would have 6 unknowns there because the wall prevents all translation and all rotation. And just like in chapter 5, I could solve for all 6 of those unknowns. Then I could make my internal cut, and then I could solve for those internal 6 unknowns that are going to be introduced. But like we saw in some truss problems, we can kind of cheat a little bit or short circuit the problem if we can make that internal cut and be able to take a side of it that doesn't have any external forces or external connections. If we look here, if I make that cut through C, I can take everything to the left of my cut or everything on my object to the right of my cut and get the same answer. If I make a cut through C and I take everything to its left, I will need to know what's happening at A before I know what's happening at C, because this will have 12 unknowns in it, the 6 at A and the 6 at C. But if I make that cut through C and I take everything to the right of that cut, well, to the right of the cut, there's no external reactions. I have F1, F2, which I'm given, M, which I'm given, and then I'm going to be introducing 6 unknowns at C, but I'm also going to get 6 equations out of it. So I can actually start with the internal cut here, if that's all I'm interested in, is what's happening internally at C. I can get away with not making an external free body diagram or solving those 6 equations. Now, if I were asked what were the reactions at A, then I would need to do that. But in this particular problem, I'm not. So I'm going to skip that step and reduce the number of equations I have to take in half. I'm going to use the same given coordinate system. I'll just shift it so that the origin is at the centroid of point C. But I'm not going to reorient it since it's already provided to me. So I'll start externally what's happening. I have these 2 applied forces, F1, F2, which I'm told what their values are. F1, negative 24I minus 10K pounds. F2, negative 80I pounds. And I have this applied moment around the negative Z axis as well. That's negative 30 around the K axis pounds, pound-feet. From C to where the elbow is going to be 2 feet. And from the elbow to where F1 is being applied to point B is going to be 3 feet. Or I could put the coordinates of where these are acting just like we saw before in chapter 5. Now at C, this cut surface is where I have to, because I detached it from the rest of the material, have to include what are those internal reactions that were keeping the material together. I'm going to start by putting the internal normal force P. Again, it always comes out from the surface of the cut. It doesn't care what coordinate system I'm using. So it's going to be pointing to the left, and I don't know its value yet. I'll call it P. Now, looking at it in terms of the coordinate system I'm using, it does go along the negative y direction, but I chose its direction because that was the outward normal from the surface of the cut. So that's my normal force. The xz plane is cutting this surface, so my shear force is going to be pointed somewhere in the xz direction. So out of convenience, what I do is I take that one shear force and I break it down into components along the axes that are parallel to the surface of my cut. So I'll have some component along the x, I'll call Vx, and I'll have a component along the z that I'll call Vz. So those are the 3 internal forces I have, 2 components of shear and my normal force. Now I go on to my couples. I have a torsion, I have 2 internal bending moments. The assumption about the direction of torsion, I use the right-hand rule, and I put my thumb in the direction of the force P, and then the way my fingers go are going to be the direction I assume that torsion T to be going. So again, I'm assuming T is positive around the negative y-axis, which is to say I'm assuming it's clockwise around the y-axis. Again, T's direction is based on P. P's direction is based on the outward normal of my cut surface. Right, so T is taken care of, and then my two components of bending moments are going to match my two components of shear force. I'll assume I have a component around the x-axis, I'll call mx, and a component around the z-axis, I'll call mz, and I'm going to assume they're both positive around the x and then the z-axis, respectively. So the assumptions about Vx, Mx, Vz, Mz are based on my coordinate system. My assumptions about P and T are not based on my coordinate system. They're just based on the direction out from the surface of my cut. I've introduced 6 unknowns, but I can get 3 force equations and then 3 moment equations out of this picture. Taking this, I now can go to my equilibrium equations and use the free body diagram to get my forces and my moments. In the x direction, I'm going to have a negative 24 pounds from F1. I have a negative 80 from F2. And now I'm assuming Vx is along the positive x direction, so a plus Vx. And it turns out my assumption for Vx is correct. Vx is a positive 104 pounds. In the y direction, I have nothing from F2. I have nothing from F1. That's a moment, so it won't get included here. I have negative P acting along the y direction. Therefore, my internal normal force P is going to be 0 at this point. And in the z direction, F2 has nothing in the z. I have a negative 10 from F1. I've assumed Vz is up. And I get 10 pounds for my component of shear force in the z direction. My 3 force equations are done, and I found my 3 internal forces. No internal normal force. It's not in tension or compression at this point. And then my 2 components of my shear force. Now I go on to my moment equation, the same way we looked at it in Chapter 5 with 3D rigid body equilibrium. I'm going to take the sum of moments around a point, and for these, it's always going to be easiest to take it about the centroid of that cut surface. And I know it's going to sum to 0, or more specifically, the 0 vector. I start again with that vector equation, and then get 3 scalar equations out of it. So around point C, I'm going to have couples causing moments around point C, and I'll have forces that are a distance away from that centroid. They're going to be causing moments as well. I'll start with the couples so I don't forget them later. I have 3 couples at C from the internal loads, and remember I have to attach a vector with them, or a unit vector with them. So mx is around the x direction, so I have mxi, minus tj, since t is around the negative y-axis, plus mzk, around the z-axis. And in this problem, I have a 4th couple. I have that applied couple m that's around the negative z-axis as well. So I have a negative 30k also in this equation. This is in pound feet. mx, t, and mz will also come out to be in pound feet, but I have to make sure that my cross products are also in pound feet. These are then the 4 couples with their directions attached. I then have 2 forces. It's been a little while, but remember, we always use r cross f when we're in 3D. Use the vector approach, use the cross product to find these values. So in this case, I'll have the position vector that goes from C to where F2 is being applied, which does not have a name. I'll just call it E for right now. And then we'll have that and cross F2. And then we'll have RCB cross F1. So starting with F2, just because it's closer to get from C to point E, I have to go 2 in the y direction. Or if I took the coordinates of E minus the coordinates of C, that would also give me RCE. So again, 2 in the y, and then that's it. No 0 in the I, 0 in the k to go from C to E. And then my third row is just the components of F2. Negative 80, 0, and 0. This is in pounds, and that's in feet. So pounds times feet, they're going to be compatible units. Then for F1, I'll have FCB cross F1. To go from C to B, I go 0 in the I direction, I go 2 in the Y direction, and I go 3 in the K or the Z direction. And the components of F1 are negative 24, 0 in the J, and negative 10 in the K. When I expand this cross product out, or this determinant out, I'll have IJK components. I have IJK components up here. Like we saw in chapter 5, I group the like components together and rewrite my vector equation that way. So I get out of my i's, mx minus 20. Both have I terms. I will get negative t minus 72 are my j terms. And my k terms, I'll have mz plus 178. This vector equation is equal to 0i, 0j, 0k. So remember, I take this vector equation and I split it up into 3 scalar equations because individually I set each of my coefficients I, j, and k equal to 0. And that gives me equations 4, 5, and 6. So 0 equals mx minus 20 means that mx is equal to 20 pound-feet. Setting my j coefficients equal to 0, I will get that t is equal to a negative 72 pound-feet. And my k coefficients equal to 0, I will get that mz is equal to a negative 178 pound-feet.